So we're going to be talking about variables, and variables are really at the heart of the language, but I'm already going to assume you know what a variable is. What's beautiful about Go is I don't have to really sit down and teach you syntax like you've never seen it before. I want to talk about the things that are not necessarily obvious or the things that are going to help us be better Go developers. And in this section, the most important thing that we can be talking about, the most important thing you can understand as a software developer is the idea of type. Type is life, okay? It is. It's life. You have to understand it. And type represents two things: the amount of memory that we're going to be reading and writing and what that memory represents. Without these two things, there is no integrity, right? And I promise you, one day after drinking about 4 or 5 whiskeys, I'm going to go to the tattoo parlor. I'm going to get type life right here, man. It's going to be type life. That's how important it is. So let's talk about type as it relates to variables in Go. And if we do this, look, our basic unit of memory, Go is a byte. And that byte represents 8 bits. So here's an arbitrary byte in memory here in Go. And there's a bit pattern over 8 bits, right? And if I asked you what this byte represented in terms of a value, you wouldn't be able to tell me until I told you the type information for this. Because until I tell you type, this is just an arbitrary set of bits. Now, if I told you that this byte represented a 1 byte integer, then you could say, oh, Bill, that represents the number 10. Beautiful. But what if I said, no, it doesn't really represent an integer, it represents a color. Now you'd have to say, well, Bill, what color is on your chart for the number 10? And I might say, oh, that's the color red. Boom, now it represents red. And this is why type is so important, because it tells us not just how much memory we're going to read and or write, but it also tells us what this memory represents, and that's where we're going to get all of our integrity from. So if we come in here now under variables, and we're going to see, and you're going to see this in all these sections, we're going to have our notes, we're going to have links for extra reading, we're going to get to our code review, we're going to jump into the Go playground. So let's do that, and I'm going to expand this out a little bit more, and I want us to look at these variable declarations between lines 15 and 18. Now again, I'm not teaching you what a variable is, you know what it is. It's a way of providing a name to some memory allocation like this to be able to reference it, because to access things by, let's say, address will be too difficult for us. But Go, if we're looking at these variables right now, there's 3 classes of types in Go. There's the built-in types, there's the reference types, and there's our user-defined struct types. We're going to be talking about all 3. Right now we're focused on our built-in types. Those are our numerics, our string, and our bool. And if you look at these variable declarations, the one I want to focus on first is on line 17. Now, what's interesting about this type float 64 is that it's giving us both pieces of information. It's telling us both that this is a 64-bit wide, right, or 8 bytes of memory allocation, 8 of these blocks that you see here, and that these 8 bytes represent an IEEE 754 binary decimal. It's a float here in Go. See, what's beautiful about this type name is it's telling us both pieces of the type information. But if you look at a type like bool, it's really just telling us representation, right? Like it's a Boolean, it's a true or false. We know that that represents 1 byte of allocation, and really we only need 1 out of those 8 bits to represent true or false. And int's also interesting because Go does have int 8, has int 16, it has int 32, it has 64. You can be precise with your integer, you can do that, but most of the time if I was doing a code review and you were using a precision-based int, probably if it wasn't obvious to me, the code review would stop. And when I talk about code reviews, you're going to hear me use the word obvious or reasonable, okay? There are times where it is obvious to use a precision-based integer. We'll see some of that when we get into writing multi-threaded code in Go. But most of the time we want to just use int. Int's just saying that we're representing integers, but it's not telling us size. And remember what we talked about in section 1, how every line of code you write is either allocating, reading, or writing to memory, and it's integer-based memory. And again, we want to be sympathetic with the hardware. So if everything you're doing is integer-based reading and writing, don't you want to use the most efficient integer for the architecture that your code is running on? Yeah, we all do. And so since the most efficient integer is based on an architecture, we don't want to use a precision-based int. We just want to say int and let the compiler choose the right precision for us. So if we're on a 32-bit architecture, then a 32-bit or 4-byte integer is going to be the most efficient int. If we're on a 64-bit architecture, then our 8-byte or 64-bit integer will be our most efficient int, and we want that int to represent the most efficient. That's why we're doing that. Of course, there are times where we have to be very explicit. In other words, it doesn't matter what the architecture is. We need an integer of a certain width. That's why we have our precision-based options. So in this case, when it comes to Go, what we're going to do is base everything on the size of the architecture's address. So if we're on an AMD 64 architecture, which I'm running on my laptop, that means addresses are going to be 64-bit or 8 bytes. Our integer is going to follow along with that, and our word size is going to follow along with that. And when you hear me use the term word, what we're talking about is a generic allocation that can hold either an integer or an address. You'll hear me using that all the time. If we're on a 32-bit platform like the Playground is, the Playground uses an AMD 64P 32 architecture native client. That means everything is 64-bit except for addresses. It uses a 32-bit memory address scheme. Then addresses of 32 bits or 4 bytes. Our integer will be 32 bits or 4 bytes, and our word size will be 32 bits or 4 bytes. So anytime we're on the Playground, we just consider that to be a single-threaded 32-bit environment. And when I'm running on my machine natively, we're on a multi-threaded 64-bit environment. We know that the size of that int is going to change for efficiency. Now again, we talked about integrity being our highest priority, and one thing Go has is called zero value. Zero value means that memory, once allocated, has to be initialized. If we don't specify the initialization state, then the compiler will initialize it to its zero value state. In other words, the compiler will come in, take that byte of memory we're allocating, and say, oh, no. I don't care what bit pattern is in there right now. What we're going to do is set it all to 0. That's that zero value idea. Now, you have to decide when you're declaring a variable, like in this case, you're going to know up front, do we want its 0 value initialization or something else? And one of Go's warts, I think it's a big wart in Go, is when there's too many ways to declare variables in Go, just too many ways, right? And a good part about code is the consistency that you can bring to it. As a team, right? Even though the language is small, there are still places like variable declarations and value construction where things can be inconsistent. So what you're going to see in the code base, and what I recommend, is that we use the keyword var to denote a zero value construction. So on lines 15 through 18, you can see the use of var with our built-in types int, string, float, and bool. And what that's telling us as a reader is that we're going to be declaring that 4 or 8 byte integer set to its 0 value. We're going to declare that string set to its 0 value, which is an empty string. That float will be 0. That bool will be false. And if we talk about strings as well, it's a built-in type, but strings can be implemented in many, many different ways. And Go has its own kind of unique implementation for a string. And when we talk about strings in Go, we're talking about a value that will be a 2-word value. Now, you hear me starting to use the term word. Remember, a word is a generic allocation. In the case of the Playground, it will be a 4-byte allocation. In the case of my machine, it will be 8 bytes, and it can represent either an integer or an address. And in the case of our string, the first word in this 2-word string value will be a pointer. So when we're set to our 0 value, that pointer will be nil. And the second word is an integer that represents the number of bytes for a string. And in case in its 0 value, it will be 0. So this would be a 0-valued string, or what we call an empty string in Go. Okay, empty string right there. 2 words. We know the size of it's fixed, but it really ends up being multiple data structures, as we'll see in a second. So we're going to use that var for 0 value. Now, what if we don't want 0 value? What if we want to initialize that variable to something else? Well, this is where we're going to use the short variable declaration operators. That's what you see between lines 27 through 30. And A lot of people think that the syntax for Go comes from the C programming language. I mean, some of it does, but a lot of it also comes from Pascal. And here's one of those areas. So the short variable declaration operator, what it does, it's a productivity operator. It will both declare, okay, and construct that variable at the same time with some initialization that's being set on the right-hand side of that operator. Now you can see here that we're setting AA to be 10. Compiler knows 10 is an integer, and so AA will be a variable of type int. Same thing with the string for BB, same thing with the float, same thing with the bool. Now, there are people who will be very explicit using the short variable declaration operator and say, well, Bill, I'd rather do this than var. And I'm going to say to you, that's fine and it's fair as long as you are consistent and everybody's consistent. I will make you a promise. If you use var for 0 value and the short variable declaration operator for anything other than 0 value, then what we're going to end up with is a code base that is much more consistent and much more readable. So let's go back to that string, because this isn't an empty string anymore. This is a string set to something other than its 0 value. It actually has hello. In the case of the string now, we're going to have 5 bytes, H-E-L-L. Let's add another byte there, hello. And our pointer here now is no longer going to be nil. It's going to point to the beginning of that allocation. And since there's 5 bytes, we're going to say 5 right here. So now this is a string that's not set to its 0 value. This is the string that we have right here. It's the BB string, and it has the 5 bytes for hello. OK, the last thing here that we're going to talk about is the idea that Go has conversion over casting. Conversion over casting, OK? And the idea of casting is this. Casting is really, it's a performance type of operation. Lots of languages have it. I mean, the idea is, let's say that we allocated a 1-byte integer. Here it is. And we decide one day that, no, we don't want this just to be a 1-byte integer. We want this to be a 4-byte integer. But we're not going to allocate a 4 bytes. We're just going to assume that these other 3 bytes right over here is OK. And suddenly we tell the compiler, hey, look, I know I've only allocated a 1-byte int, but let's pretend it's a 4-byte integer, and let's read all 4 bytes. That could be OK, but it could also be very, very bad. And so the idea of casting has usually cost us a lot of bugs over time, because we overlay probably a structure. More than an integer, we probably overlay a structure over this memory. Like some memory comes over the wire, you plant it there in memory, you overlay a structure, we cast a structure over that memory. And if we're off by even 1 byte, we're going to have serious problems, right? So Go understands this. Casting is very complicated. It can produce bugs. And we still have the unsafe package in Go to do this. But the idea is, instead of taking the risk for casting unless we absolutely need it, let's do conversion. And what conversion says is, let's not try to read all of these bytes, but if we have this 1 byte here and we want to convert it to a 4-byte integer, let's just allocate the 4 bytes we need. And we'll just kind of copy or move that value. Instead of over 1 byte, we'll move it over these 4. It's a new allocation, but it is much safer to do it that way. And you can see the conversion syntax on line 38, where it looks like a function call against the type. So here we're saying, let's convert the value of 10 to an int 32, and we'll get this type of allocation that you're seeing here on the conversion. All right, so remember that Go hasn't eliminated casting. You can still get to it from the unsafe package, but as a core part of the language, conversion over casting, because integrity has to matter more. So as we're done with this section here, let's just recap, OK? Go has its built-in types. It's got reference types we're going to talk about. It's got struct types, variable declarations. There's way too many ways to do it in Go. So we're going to use the var keyword, like you see on lines 15 through 18, to represent 0 value allocations. That's Go setting all those bits. We're going to use the short variable declaration operator for anything other than 0 value. This is a coding standard that we're going to be using throughout this video. And then Go has conversion over casting. And remember, type is life. Type tells us 2 pieces of information: size, the amount of memory in bytes that we're going to be reading and writing, and its representation. And this is where we get a lot of compiler protection from. By knowing our type, we can make sure that every read and every write has integrity. Remember, accurate, consistent, and efficient.